Characteristics of linear optimization models. We keep using linear programming models and integer programming models or nonlinear programming models. But how do we know that a model that we develop is a linear programming model? Well, if the objective function and all constraints that you defined in that model, those are all linear functions, then you get yourself a linear programming model. Okay, so in order to decide whether your model is linear or not, you have to check the objective function and all the constraints that you have in that model. If they are all linear functions, then your conclusion is yes, that's a linear programming model. If not, if any of the constraint or the objective function has a nonlinear term, then that problem is not definitely a linear programming model. Okay, and also if the domains of the decision variables are integer, some of them, then that wouldn't also make a linear programming model, because all variables in your linear programming model must be continuous, meaning that fractional values are allowed. So the integer programming model might have some integer values, but in that case that wouldn't also make this problem a linear programming model. The question here is that how realistic is this assumption? So should all of my decision variables be continuous, meaning that they can take up fractional values? Well, let's go back to this example, the ski company example, as we defined our decision variables here as the number of journal products and the number of Tiercraft products, right? So what does it mean to have fractional values for these products? So let's assume that Tiercraft's models at the optimal solution is 3.5. What does this really mean? So can I have 3.5 ski, right? I cannot, simply I cannot. So therefore this is not really a realistic assumption. But then why do we have to deal with linear programs? Because those are easier to be solved compared to integer programs, okay? So if you get fractional values, let's say at the end, you can always run them up or down based on your constraints. And also there's often a quick trick that you can implement if your objective function or your constraint is nonlinear. Right? So for example, the most common trick that we use is to convert the ratio constraints into a nonlinear ratio constraint into a linear one. So in this example, we have the constraint that says if two ingredients contain 20% and 33% of nitrogen respectively, then the fraction of nitrogen in a mixture of X pounds of the first ingredient and Y pounds of the second ingredient is expressed by the constraint function of this. Okay, X and Y is the total, and then 20%, 30% of X and Y can be written as in the numerator. And this constraint, as you can see, is nonlinear. But what you can do is that, okay, at the end there is also a continuation of this constraint. It says that if a constraint requires that the nitrogen fraction to be 30%, this can be written as a linear function, because the 30% of nitrogen can be equal to this one, right? So if you rearrange the terms, you can easily get this linear function. So it's originally nonlinear, but now we can make it linear. Okay, this is just a quick transformation.